Hello everyone. So here we are again with another topic, that is effect of ductility and brittleness on stress concentration. Okay. So moving on to the topic, let us just have an overview on effect of ductility and brittleness on stress concentration. Okay. So stress concentration has negligible effect on the ductile materials subjected to static loads. Under the static load, when the stress near the discontinuity reaches the yield point, local plastic deformation takes place, okay, and the stresses get redistributed, relieving the stress concentration. Okay, so what happens when stress concentration has negligible effect on ductile materials subjected to static loads? Then the stress near the discontinuity reaches the yield point, okay, and plastic deformation, or that is local plastic deformation, takes place, and the stresses get redistributed, relieving the stress concentration. Okay, therefore ductile materials subjected to static loads are not affected by stress concentration, and there is no need to apply stress concentration factor to statically loaded ductile materials. Okay, so therefore ductile materials subjected to static loads are not affected by stress concentration, and there is no need to apply stress concentration factor to static loaded ductile materials. Okay, moving on to the next slide. Here we will go that but for ductile materials subjected to dynamic load, stress at the discontinuity may reach its endurance limit, leading to fatigue failure. Okay, therefore stress concentration reduces the endurance limit of ductile materials, and stress concentration factor must be used for dynamically loaded ductile materials. Okay, this aspect will be discussed in the next lesson. Okay, so for ductile materials subjected to dynamic load, stress at discontinuity may reach its endurance limit, leading to fatigue failure. Therefore stress concentration reduces the endurance limit of ductile materials, and stress concentration factor must be used for dynamically loaded ductile materials. Okay, next, stress concentration has more severe effect on the brittle materials due to their inability to plastically deform. Okay, as there is no local yielding, stresses don't get redistributed, and local stress due to discontinuity increases highly. Therefore stress concentration factor must be used for components made of brittle materials subjected to static or dynamic loads. Okay, so here what happens for brittle materials? Okay, stress concentration has severe effect, okay, due to the property that the inability to plastically deform. Okay, because ductile materials may be plastically deformed, but brittle materials, they don't have plastically deformed properly. Okay, so as there is no local yielding, stresses don't get redistributed in brittle materials. Okay, and local stresses due to discontinuity increases highly. Therefore stress concentration factor must be used for brittle materials. Okay, next, creep. Okay, so now let's have a look what is creep. When components are subjected to constant loads continuously for a longer period, they may undergo progressive elastic deformation over time. Okay, this time dependent strain is called creep. Okay, creep can be defined as slow and progressive deformation of material with time under constant stress. So what is creep? Creep can be defined as slow and progressive deformation of material with time under constant stress. Creep deformation is a function of stress and temperature. It generally occurs at absolute temperatures above half the melting point of the material and is even present at room temperature for materials like aluminium, copper and some plastics. Creep increases with the increase in temperature and therefore becomes very important for components operating at higher temperatures like those of furnaces, steam and gas turbines, internal combustion engines, nuclear reactors, rocket engines, etc. The stress can be tensile, compressive, bending or shear. So from here what we have found out that what is creep. Okay, so creep can be defined as slow and progressive deformation of material with time under constant stress. Okay. Next, components operating at higher temperatures must be designed in such a way that deformation due to creep remains within the allowable limit, and also creep deformation doesn't lead to rupture, so that the product performs satisfactorily over time. Okay, so creep strength and creep rupture strength are the two important properties of the material related to creep design. Okay, so the two important properties that have been related to creep design are the creep strength and the creep rupture strength. Okay, so creep strength, what is creep strength? So creep strength is the maximum stress that the material can withstand for a specified length of time without excessive deformation. Okay, so creep strength is the maximum stress that the material can withstand for a specified length of time without excessive deformation. Okay, so creep rupture strength is the maximum stress that the material can withstand for a specified length of time without rupture. Okay, so the two important properties of material related to creep design are creep strength and creep rupture strength. Okay, so the maximum stress that the material can withstand for a specified length of time without excessive deformation is called creep strength. Okay, and the maximum stress that the material can withstand for a specified length of time without rupture is called creep rupture strength. Okay. Okay, next, here in the next slide we will see a figure that shows a typical strain versus time plot, which is known as creep curve. Okay, so to obtain creep curve, specimen is loaded with a constant force and variation of its length is observed at a constant elevated temperature. Okay, so units of strain are mm per mm, that is unitless, and time is measured in hours. When the load is applied in the beginning of the test, some instantaneous elastic deformation or initial strain occurs. Then, with the passage of time, creep strain occurs. Creep curve is divided into three stages: primary, secondary and tertiary creep, after which the rupture takes place. In the start, strain increases rapidly, known as primary. In the second creep, strain increases slowly at a constant rate. Okay, again during the tertiary stage, strain rate increases and necking of the specimen takes place, followed by rupture. The creep test is repeated over a range of temperatures to obtain a number of creep curves that are useful for design purpose. Okay, so here you can see the figure, the creep curve. Okay, so here it is the, you can see the creep, primary creep, it moves in this direction. Okay, then it goes to secondary creep. Okay, so here you can see the constant slope, that is del epsilon by del t, which is the strain rate. Okay, so here you can see the strain rate. Next it goes in this manner, and here the tertiary creep occurs. Okay, so after that the tertiary creep, the point originates, which is known as the rupture. Okay, so here you can see for the initial strain, that is from 0 to epsilon naught. Here you can see the initial strain, and from epsilon naught to epsilon r, here it is the creep strain. Okay, so and here you can see the strain rate. from this slope. Okay, so this is all about creep, and this about the creep diagram. Okay, so with this we have come to the end of this lecture. Thank you everyone.